Hello there, my name is Lucas. Welcome to my channel. Do you see this group of agents? Right now they are just drifting forward, not really doing anything. But let's see what happens when we add 3 simple rules to their behavior. First, I have them steer away from each other using separation. Now, instead of aimlessly sliding forward, like they are having a midlife crisis, we've turned them into a bunch of antisocial buggers doing anything to avoid small talk. Let's fix that. We can improve their introverted behavior by adding a second one into the mix, called cohesion. This will steer them towards the center of their neighbors, pretty much telling them, maybe go outside, touch some grass and stop spending all day indoors trying to make this video. Anyway, let's go on. Third, we'll tell the agents to steer in the same direction as their neighbors. Do you see what happens? By adding just 3 simple rules, we suddenly got much more interesting behavior. The agents start to move together, kind of like a flock of birds. What I've just shown you is a simple simulation model commonly referred to as Boids. Each agent, or Boid, moves using a steering velocity determined by a set of behaviors. These behaviors can be anything. In the example I showed, I added 3 behaviors: separation, cohesion and alignment. For each of the 3 behaviors, we look at the agents that lie nearby the agent we are calculating the movement for. We call these neighbors. For the separation behavior, we subtract the position of each neighbor from our own position. We combine this into a single normalized vector. This is the direction we'll want to move in order to separate from our neighbors. In this example, I'm only doing this for one agent, but in reality, we do this for all of the other agents as well, simultaneously. Cohesion is a little different. It looks at all of the positions of our neighbors and calculates an average position. This is the position we'll want to move towards. Then last, we have alignment. This time, instead of looking at all of the positions, we look at all of the directions our neighbors are heading towards, and again, calculate the average of this. By simply applying these 3 simple behaviors to all of our agents, we can get surprisingly complex group movement. So far, I've simply shown you some of these agents on a flat plane. We can however make this a lot more interesting by moving things into a 3D space and filling the scene with some birds. Let's take a look. As they fly around, you can see them bunch up, spread out and sweep across the air in smooth waves. Almost as if the whole flock is one living organism. Doesn't that look amazing? Before this turns into a nature documentary, however, I'll quickly move on. With just 3 simple rules, we've been able to simulate a whole flock of birds through the sky. This is far from the only thing we can do with this, however. I've merely scratched the surface. So before you think, is that all, and click away, wait, keep watching, because I would love to show you more. First, allow me to explain how this all works. Like you probably already guessed, we have an agent. This agent contains a few core properties. A position, a velocity, plus 2 limits. The maximum force and the maximum speed. Every agent also contains a list of behaviors. If we take a closer look at the behavior class, we can see that each behavior returns a steering vector. This is the direction that the behavior will try to move the agent in. Behaviors also have a weight property. This weight property lets us control how strong each behavior is. Since we will have multiple behaviors, all trying to steer the agent into a certain direction, the weight allows us to balance which behaviors should have the most impact on our agent's movement. Let's go back to the agent. Each frame, we calculate the combined steering force by looping over all of the behaviors. We then add the force to the agent's velocity and clamp it, so it doesn't exceed our agent's maximum speed. We then apply that velocity to our agent's position. Let's take a closer look at how we combine our behaviors into a steering force. We loop over all of our behaviors and add each behavior's output to a single vector. If we want to adjust the effect a behavior has on an agent, we can simply increase or decrease the weight property. We can increase it as much as we like. Notice that when we do so, the final steering vector never exceeds our agent's maximum force. Right now, all we use is a single weight property for balancing out our behaviors. This works, but as we start adding more and more behaviors, it becomes increasingly more difficult to keep this balanced. So instead, we introduce behavior prioritization. To help me demonstrate, I'll add a 4th behavior. This behavior, named obstacle avoidance, steers the agent away from any obstacles in the scene. Right now, it barely affects the agent. We could increase its weight, but we need an absurdly high value to make it work. Instead, we give behaviors an additional priority property. The higher the priority, the earlier the behavior is considered. Since the obstacle avoidance behavior is the most important, we'll increase the priority of this behavior, so it will be considered first. We will make a small change to the way we combine our behaviors now. We shall introduce a variable called remaining force. As you know, each behavior returns a steering vector. The length of this vector is subtracted from our remaining force every time we add it. Once we run out of remaining force, however, we will stop evaluating any behaviors that come after it. This ensures that the most important behaviors always take an effect. Most of the time, we'll reach the end of the list, but if something like an obstacle avoidance behavior outputs a very large vector, probably because the agent is almost colliding with an object, we immediately run out of remaining force. Only once the avoidance behavior no longer outputs such a large vector because the agent has steered clear of any obstacles, will the other behaviors be considered again. Now that we've got that out of the way, let's do something cool again, shall we? Do you see this body of water? We can fill it with a bunch of fish, but first we need an obstacle avoidance behavior, otherwise our fish will smash their pretty little heads into the rocks. In order to help our agent avoid obstacles, we should race outwards at an increasing angle until we find a safe direction. This direction will be the force our behavior outputs. In 3D, however, selecting ray directions is a little trickier, so we use a function that evenly distributes points on a sphere. We can use the coordinates of these points for our ray directions. If you'd like to know more about how this works, I recommend you to watch Sebastian's video. I'll add a link to this in the description. Now our agent should be able to avoid obstacles. I've created the scene with a single agent to demonstrate what it looks like in 3D. We are now ready to populate our body of water with a bunch of fish. See how they flock together, yet simultaneously manage to avoid obstacles in their way? This shows you the power of the simulation method. It allows us to combine a bunch of different behaviors in order to simulate group behavior. You can easily apply this to crowds as well, or maybe an RTS game for example. As we increase the size of these groups, however, we will start to run into some issues. Remember that I told you that the 3 core behaviors look at the neighbors of an agent. For this, we'll need to know which agents lie in a certain range from each other. Currently, the way we do this is pretty inefficient. We take a look at the agent we need to get a list of neighbors for, and check the distance between it and every other agent in the scene. We then repeat this step for every other agent in the scene. Oh boy. As you can probably guess, this takes a long time. And since we also have to lose every single frame, our frame rate is soon going to be worse than Cyberpunk when it first got released. We're gonna solve this, however, by doing something called spatial partitioning. Instead of doing a distance check for every single agent, we are going to create a grid and store our agents per cell. Now, if we want to figure out the neighbors for our agents, we'll only have to look at the agents that lie in the cell that are overlapping with our range. This is much more efficient than we did previously and allows us to simulate much larger crowds than before. Awesome! Now that we've got that covered, let's do something different. Do you see this kitchen? It looks like the owner dropped some cheese on the floor and forgot to clean it up. Let's infest this kitchen with some mice. These mice are having a great time, but this all changes once the cat comes in. Due to the fact that the mice currently have no idea how to avoid this predator, they currently just keep going about their business, and get eaten in the process. Let's write a behavior for them that will help them evade our predator. We could of course just make all the mice run in the opposite direction of our predator. We can however make them a lot more smarter with just a small tweak. Instead of making them run away from the predator position, we offset this position in the direction our predator is heading and multiply it by our predator's speed. This will cause the mouse to predict where the cat will go next and then run away from that position instead, causing them to always be a step ahead and avoid becoming the cat's dinner. Quick thing, before we implement this yourself however, make sure to clamp your agents to the floor plane. Otherwise, your mice might begin to fly. I decided to go ahead and give him a cape and called him Super Mouse. Yes, now the cat will never be able to catch him, cause cats can't fly, fuck. So far, I've shown you a handful of cool things you can do with Boids. But, as you can probably imagine now, there's still a lot more you can do with them. Why not check it out for yourself and see what you can come up with. To help you out, I've added the link to the project in the video description. If you enjoyed this video, please be sure to leave a like and consider subscribing. I am also very curious what topic you'd like me to cover in the next video. So, if there's anything you'd like to know more about, please let me know in the comments. That'll be all for now. I want to wish you a good morning, afternoon, evening or night and see you in the next. Goodbye.